Sorry. And we start to broadcast. Okay. Good morning, everybody. Welcome to the second day of the Ultrafast X-ray Summer School 2020. I hope you had some good meetings with your mentors yesterday. I apologize for the technical hiccups we have initially, but that's kind of part of my and our learning cycle. Before I introduce the first speaker of today, I want to give you a quick overview over the schedule for the day. So we have the second lecture in the beginning. Then we have a break, and that's gonna take place exactly the same way as yesterday. You'll get into a break Zoom meeting and get distributed into smaller groups. Then we have the third lecture, another break, and then we have the lecture office hours. Today it's for 3 lectures. Giorgio Margaritondo, who gave the first lecture yesterday, and the 2 lecturers today, Sankyo Son and James Crine. And you can find the Zoom links for these lectures also again in the Canvas course calendar on Stanford Canvas. Then we have a very brief break, and then again, proposal mentor office hours. I hope everybody has now a current Zoom link to these office hours. If you have the Zoom link and you don't see it posted on your Canvas group page, please post it there so that everybody gets this link. And if anybody doesn't know where to meet for the mentor office hours today, please shoot me an email. With that, I have to stop sharing. With that, I want to hand over to our first lecture for today, giving the second lecture of the summer school. It's Sankyo Son from Hamburg, from CFL. I'm very glad that he agreed to give the lecture on theory of X-ray matter interactions. Sankyo, I'm very happy that you're here, and yes, I'm very interested in your talk. Please go ahead.
Thank you. Thank you for kind introduction. And good morning, good afternoon, and good evening. So my name is Sankyo Son, and working at the CFL Center for Free Electron Laser Science, located at DEGI, Deutsches Elektron and Synchrotron in Hamburg, Germany. It's my great pleasure to meet you guys and giving a lecture about the theory of X-ray matter interaction. Here is the outline of my lecture. So first part is about the basics of X-ray matter interactions. We will start with the Hamiltonian and transition rate. And I will cover the most of X-ray induced processes like X-ray absorption and decay processes and scattering and so on. In the second part, after the short break, in the second part, we will see what happens if X-ray intensity is so high, presenting some case studies of AMO physics in X-ray fields. Okay. How do we treat interaction between X-ray and matter? So total Hamiltonian is expressed like this, and the molecular Hamiltonian and free electromagnetic Hamiltonian, and the interaction Hamiltonian. Interaction Hamiltonian between them. And we will use atomic units unless it's specified with a different unit. Well, note that X-ray interact with the electrons only. So we will focus on the electronic Hamiltonian in the molecular Hamiltonian. And we will employ non-relativistic quantum electrodynamics and the principle of minimal coupling. For calculating the transition rate, we will use time-dependent perturbation theory. Okay, well, Hamiltonian for free electromagnetic field is written like this form, a sum of uncoupled harmonic oscillators. For each mode, for each mode here, the k is the wave vector, and epsilon k is polarization vector, and omega k is angular frequency. The field operator A here is the annihilation operator. Just take out the one photon. And therefore, the n photon state here becomes n-1 after applying the annihilation operator here. And the field operator A dagger indicates the creation operator. So after applying the n photon state, it becomes n+1 after applying the creation operator. So the electromagnetic field operator satisfies the commutator relation like this because the photons are bosons. The next, the molecular Hamiltonian is expressed like this. The sum of the nuclear kinetic Hamiltonian and the nuclear repulsion and the electronic Hamiltonian. After we apply the second quantization, the electrons may be interpreted as an excitation of a quantum field. So here, the psi, well, psi is it has a two component, like a psi spin up and spin down. It's a two component, and the psi sigma indicates psi sigma here, for example. Well, it indicates annihilation operator, annihilation of an electron at position x with a spin sigma. And psi dagger here, the sigma, is the creation of an electron at the position x and the spin sigma. The electron field operators satisfy the anti-commutator relation because they are fermions. And the exact electronic Hamiltonian here is consists of the kinetic energy and the electron-nucleus interaction and electron-electron interactions. Then, how do we describe the interaction Hamiltonian between the photons and matter? So after applying the minimal coupling and the Coulomb gauge, it is expressed like this form here. Here, the A is called a vector potential, which is the sum of modes, mode K, and each mode K contains annihilation operator here and the creation operator there. The first term here is called P dot A, which corresponds to the change of electronic state and the one time of A operator. And A here contains, again, the annihilation creation. So that means it, well, represents the one photon absorption, that's annihilation, and one photon emission, that's a creation. If the P dot A term is applied 2 times, then it becomes second orders. Now it can describe the scattering process, like one photon in and one photon out. And second term here, it's called A square term, and it's already like 2 times of A. So that's why it can describe, the first order of this term can describe a scattering process, like photon in and photon out. How do we calculate the transition rate? We will use time-dependent perturbation theory. the molecular and free electromagnetic Hamiltonian becomes, this and this term becomes unperturbed Hamiltonian, and the interaction Hamiltonian is the perturbation. And initially, we have n electron and n photons. The state vector in the interaction picture is formulated like this, and well, it's up to the first order and second order. Then the transition rate is calculated with this form. Again, here is corresponding to first order and second order. So now let's talk about the X-ray absorption. When X-ray is observed by a many electron system like this, and it kicks out an inner shell electron here, because, well, the X-ray usually has enough energy, resulting in the inner shell vacancy like this. And so the initial state here is n electron, n photon system. And the final state is, well, electron state becomes psi f, and it's a one photon observed. So it becomes n-1 photon here. Absorption rate can be calculated within the first order only. So we take only the first order. And if we know the initial state energy here and final state energy and initial state and final states, and if we know the form of interaction Hamiltonian, then we will be able to calculate the absorption rate. So let's do it. Here, once we plug in the interaction Hamiltonian, then the rate expression becomes like this. And here, note that only the P dot A term is used, because the number of photon, the change of number of photon has to be just 1. So that's why we just use the P dot A term in the interaction Hamiltonian. And this rate is proportional, linearly proportional to the photon flux here. So since we are interested in some quantity which is independent of incoming photon flux, so we define the cross section as the rate divided by the photon flux here. This cross section is expressed like this form here. And now the question is, what do we do with this total wave function here, the final, and there in the initial? How do we treat many electron system? That's the big question. Well, we introduce a set of spin orbitals, which are eigenstates of an arbitrary electronic one-body Hamiltonian. This one-body Hamiltonian F can be written as the sum of the spin orbital P here. And CP here basically means to remove an electron from the spin orbital P. And the CP dagger here is to put, it's a creation operator, so to put an electron into the spin orbital P. CP and CP dagger satisfy the anti-commutator relation like this, because again, electrons are fermion, and these spin orbital operators are connected to the electron field operator here. The exact electronic Hamiltonian can be approximated by this one-body Hamiltonian F. And F contains only one-body interaction, but all the other two-body interactions, such as Coulomb interaction and so on, are treated as a mean field. So this is called independent electron model or the mean field model. So total wave function psi is approximated by a single Slater determinant. phi. If we have n electron state, each electron is created here, Ci dega, with created with the creation operator from the nothing. It's a vacuum state. Then the ground state energy is calculated with the summation over the all orbital energies. And there are many different ways to define a mean field, but among them, the Hartree-Fock method is the best one, in a sense that it minimizes this quantity. Well, it minimizes the residual potential between the exact and the mean field. So that's why it is considered as the best choice among the mean field model. Once we accept the mean field model, or well, more desirably, well, Hartree-Fock picture, then the final state after ionization, here the final state can be written as this form. Well, it's a single hole state, so therefore we apply the annihilation operator on ith orbital. That's gonna be our final state, one hole state. And the ionization potential, which is the energy required to ionize the ith orbital, is simply given by a negative of ith orbital energy. Well, this is an approximation, but it becomes equal if we use Hartree-Fock method. This equal relation is called Koopmans theorem. And as you can see here, the Koopmans theorem provides a very good estimate of the ionization potential for 1s and 2s 2p orbital for neon case. Now, well, let's revisit the X-ray absorption problem with the mean field model. Well, kicking out one electron from the ith orbital, and that electron goes into the 8th continuum state. This is particle hole state. One annihilation operator on ith and one creation operator on 8th. Initial state is the same, like n electron and n photon initially. And oh, well, the thing is now this is phi. That's a Slater determinant rather than the total wave function psi. The final state is written with the particle hole state combined with n-1 photon state. So now the cross-section is simply given like this expression. Now here, instead of total energy, we have ith orbital and 8th orbital. So it becomes just an overlap between the ith orbital and 8th orbital, which weighted with this. It's very much simplified, and now you can easily evaluate the cross-section from any electronic structure calculation. The kinetic energy of the excited or the ionized electron is given by incoming photon energy minus ith ionization potential, which is called photoelectric effect. Okay, now this is a simple quiz for you. So neon atom has, oh, okay.
That is
neon atom has 3 subshells, like 1s and 2s and 2p. And which electron will be ionized the most when we shine the X-rays at a photon energy of 2000 eV?
And Sankel, let me know when you want to close the quiz.
Okay, I think, well, it's not that difficult, I guess. And well, for your hint, you can see the ionization potential corresponding to the each subshell there. And well, don't forget that you have option to choose, well, no ionization happen in this case. maybe. Well, we can see the results.
You should see them now.
Aha. Okay. The most of you guys chose C, 1s orbital. Well, yes, this is correct. Most of you are correct answer. And well, let's discuss why it's a 1s orbital. The first, the 2 keV photon energy is above all the ionization potential. So ionization surely happened. And second, as we saw in the previous slide, the cross-section contains the integral between ith and eighth orbital, or the bound state and continuum state. So the radial function of 2p here is slowly changing, while the continuum state here is fast oscillation. So which makes overlap extremely small. In contrast, the 1s has a very sharp peak at the beginning here. So it makes a considerable overlap with the fast oscillating continuum states here. That's why the inner shell electron cross-section at the hard X-ray is typically higher than the outer shell electron cross-section. And that's why the cross-section decreases as the photon energy increases, which means, well, higher photon energy means the fast oscillation. Let's see a typical shape of the photoionization cross-section. And this is the neon case. And x-axis here is a photon energy, and y-axis is total cross-section in a log scale. And here is the LH, 2s and 2p, and the KH, 1s orbital. And if the photon energy is below the KH here, then the 1s ionization does not contribute to the total cross-section. When it's above the KH, well, K-shell ionization potential, then the 1s ionization contribute to the total cross-section, and that's why it has a big jump here. When the photon energy increases, then the cross-section decreases because of the faster oscillation. Okay, and here are more examples for the other elements. If you approximate the you can check out this data table in this X-ray data booklet here, or you can calculate them by yourself using the Excel. The references will be given at the end. Okay, well, let's do some the useful practice. If you approximate the bound states as the hydrogen-like wave function, and the continuum states as the plane wave. This is a hydrogen-like wave function and the plane wave for their continuum states. Then you can obtain analytical solution for the cross-section, which is, well, proportional to the fifth power of G. That makes a big contrast between the light atom and heavy atom. And it also inversely proportional to the omega, the incoming photon energy, to the 3.5 power. So it makes decreasing as omega increases, as we saw in the previous slide. And well, what can we do with the X-ray absorption? It's a quite huge area, and I cannot cover all of them, obviously. But the more fascinating examples, like time-resolved probe the absorption spectra and so on, will be covered by the Marcus Goer's lecture on Thursday. And let me point out two big categories: X-ray photoelectron spectroscopy, measuring the kinetic energy of ionized electron, and X-ray absorption spectroscopy, measuring the absorption cross-section as a function of photon energy. There are two big categories. The most evident example for the photoelectron spectroscopy is ESCA, the electron spectroscopy for chemical analysis. This molecule here, aka the ESCA molecule, has 4 carbons, and the chemical environment for individual carbon are all different. When we shine the X-ray with one fixed photon energy here, we detect photoelectron and measure the kinetic energy of photoelectrons. They are reflected by the different ionization potential here, according to the different position and different chemical environments. That's what you can see as a chemical shift in this ESCA spectrum. In the X-ray absorption spectroscopy, we change the incoming photon energy, and we measure the photoabsorption cross-section. The cross-section is obtained measuring the measurement of the transmission in a solid target, or the fluorescence measurement in a gas phase or the very dilute target. This is the typical absorption spectra, as we already saw before. So nothing happened here, and a big jump at the edge, and slowly decaying here. Once we look at some details here and there, and we learn some additional information. For example, here, when we focus on the near edge, we could learn the local coordinate environments and the oxidation states of metal species and so on. This range is called JANE, X-ray absorption near edge structure. This range here is highly sensitive to the nearest neighbor geometry and the change in the bond lengths and so on. This is called EXAF, extended X-ray absorption fine structure. Well, to give you a hint, the keyword is NE, near edge, for here, and E, extended in this area. Well, don't forget that, because, well, I mean, this JANE is also called NEXAF, that is near edge NEXAF, near edge X-ray absorption fine structure and so on. So the NEXAF, EXAF, there are all the different names, so just be careful for that. Alrighty, so now let me just talk about the fate of inner shell vacancy after X-ray absorption. After the photoabsorption here, it creates inner shell vacancy, which is energetically highly excited. So it has to be relaxed. How? Well, one valence electron is filled up the core hole, and the excess energy between them is released by emitting one photon here. This is called fluorescence. Or the one valence electron goes down to the other core hole, and another valence electron is ejected with excess energy. This is called Auger decay. In the following slides, we will see how we can treat them theoretically. the first, the fluorescence picture. So we start with cohort state. So initial electronic state is obtained by applying annihilation operator on the selected determinant, the psi. Psi of the n-electron system. That's the initial electronic state. And well, let's say no photon initially. So it's a vacuum. The final state is here, final state here, the one vacancy in the valence shell. So, and then one photon is added. So that's why, well, here is an n-electron system, but annihilation operator on I prime orbital, which is different from I, and one creation operator with the fluorescence wave vector, KF. Once we define the initial and final state, and the rate is calculated as the same way as before here. In the interaction Hamiltonian here, we will take only P dot A because only one photon is out. The fluorescence rate is calculated with the transition matrix element here between I prime and ith orbital. The fluorescence energy is given by the difference between I and I prime ionization potential, which is basically the difference between I prime and I orbital energies, according to the Koopmans theorem. Here are some examples.
Sankil?
Yes?
Can I ask a question for the audience?
Oh, yes, please.
The question is, why does an outer shell electron drop down to fill the hole instead of the hole moving up step by step?
Well, that's, I think, good question, actually. Well, okay. Well, in this case, there are not many chances. So we may not see it happens like a step by step. However, well, I will show you some figure of the heavy atom case, and then you can see it happens like a step by step. And I already give the hint for you. Well, it is called Auger cascade. So, well, yes, well, there's no reason to have the only the valence, the outmost valence electron, the fluorescence from the most the outer shell electron. That's all possible. Like all, the subshell can, well, the decay or fluorescence or Auger decay may happen throughout the all available subshells above the inner shell vacancy. That's the answer.
May I answer another question? There just came another question in. Could you also analyze this as a scattering process, absorption and then fluorescence?
Well, after absorbing one photon, then make a fluorescence. Well, overall, you can say it's a photon in and photon out. So you may say, okay, that's a scattering process. But in that case, since the fluorescence case, for example, like we have a different initial electronic state and the different final electron state. So it's an inelastic scattering. So, well, yeah, you may consider it's a inelastic, the scattering process. But, well, since the intermediate stage, in this case, like a cohort stage, is well defined. So that's why, well, we typically consider the absorption and the fluorescence separately.
And maybe a last question for this break. Is it okay to use perturbation theory if the X-ray pulse is strong and not a weak perturbation?
Oh, that's a very important question. So now, so far, as you can see, for example, here, we are treating the interaction between the light and matter throughout first order perturbation. Once we increase the intensity of the other X-ray pulse, if that's an X-ray, then, well, the dominant process will be a sequence of one photon absorption. So it is called sequential multi-photon multiple ionization. Again, that's a sequence of one photon absorption. It's because, well, in the X-ray, the one photon channel is available, always there, because X-ray photon energy is high enough. So that's why the one photon process is always available. So the cross section of the one photon absorption is much higher than the direct multi-photon process. So therefore, again, the dominant channel is sequence of one photon absorptions. That's what happens in the intense X-ray physics. I will show you in the second part, by the way. But well, also that's true that if the X-ray intensity is extremely high, then, well, we might consider the direct multi-photon process also. But again, when we think about the, well, calculate the direct multi-photon cross-section in the X-ray regime, it's extremely low.
Okay, do you want to answer one more question, or do you want to continue?
Oh, well, let's take the other one. Well,
okay.
Yeah, one more question, yes.
How do you analyze the selection rules to know the possible transitions?
Well, actually, maybe here. So, well, I just put this form, but when we do some, well, this is like an accelerated form, but if we take the, well, dipole approximation here, and then once we use the linear form here, then that becomes just nothing but like an overlap with the I and I prime weighted by R, the dipole term R. Well, I, R, I prime. Well, there, well, we can consider the selection rule. So the selection rule pops out from the overlap, well, transition matrix element. So well, yes, we have to consider the selection rule, and well, maybe that's why. Well, have you showed this slide before or not? I don't recall.
No.
Well, yeah, and that's going to be the next slide, and you will see the well, specific transition happens, well, here and there, and according to the some selection rule. So not all of them are possible, but very specific transition are possible, and according to the that specific selection rule, well, we name like a K alpha or K beta and L alpha, beta, and so on. Well, I hope that that's going to be answer for the last question then.
Yes, and there are no more questions, so please continue.
All righty. So this is the transition lines, fluorescence transition lines, and well, okay. What I want to say here is, well, this transition line provides unique energy for each element and each charge state, as you can see here. So therefore, the fluorescence can be used as a fingerprint of chemical elements. And well, this is the colorful example of X-ray fluorescence application. Using the X-ray fluorescence spectroscopy, scientists could learn more about chemical composition on Tankoff masterpiece, Sunflower, and use such information for better preservation of this masterpiece. And it's published in the Angebert Chemie, that's a science journal. Okay. And here, okay, well, let's do the same practice as we did for X-ray absorption. Using the simple model with hydrogen-like wave function, we obtain the analytical expression for K alpha photon energy here, proportional to the G square. And well, I mean, this relation is well matched with experimental data as shown here. The Moseley's law. The analytical solution for the K alpha fluorescence rate, based on the simple model, shows the rate is increasing rapidly as the force power of G. Okay, and next one is Auger decay, or well, let's start to call it Auger-Meitner decay. Even though this process is well known as the Auger decay, but the Lisa Meitner discovered 1 year before the Pierre Victor Auger discovered the same phenomenon independently. So to acknowledge her contribution, there is a renaming proposal in Physics Today recently. So if you are interested in, you can just take a look this link. Okay, the initial state of the Auger-Meitner decay is the same as fluorescence. Like from the n electron system, we just take out ith orbital, the electron from the ith orbital. And the final state is here. 2 electron is missing here and there, so J and J prime, and put 1 electron into the continuum state A. So that is expressed like this form. No photon is involved here and there. The rate expression is basically the same as before. But there is a slight difference because Auger-Meitner effect does not involve any photon. In this case, the unperturbed Hamiltonian is the mean field Hamiltonian, and the perturbation, which is expressed by interaction Hamiltonian here, is given by 2 electron Coulomb interaction. So then the Auger-Meitner rate is given as purely the electron Coulomb matrix element here with this form. Again, let's check out a simple model. I think this is important because it provides a physical insight. Here, KLL means K shell vacancy in the initial state and the 2 L shell vacancies in the final state. The analytical solution based on the simple model, the same trick like the hydrogen-like wave function and the plane wave. Then, well, the KLL Auger-Meitner, the electron energy is proportional to the G square, okay? And it turns out the rate is independent of G within the simple model. Okay, well, this is another quiz for you. For the, okay, here we go. For the light atom, like neon, Auger-Meitner decay is dominant over fluorescence, which means the Auger-Meitner rate is higher than the fluorescence rate. The question is, what about the heavy atom, like xenon? Do you think Auger-Meitner decay is still dominant, or the fluorescence catches up the Auger-Meitner rate, or their rates are more or less the same, or it won't decay for heavy atom? Which one do you want to go?
Okay, I'm gonna end the polling now.
Yes,
And this is the
see.
results.
I see. Well, most of people, like 2/3 of people, chose fluorescence. Great. Yes, it's a fluorescence.
There's also a question from the audience where people want to know if there's any approximation to know what is kind of dominant, the fluorescence or the Auger emissions. Is it the X-ray energy or is it something else?
Well, X-ray energy. Well, and by the way, well, this plot shows the relation between like fluorescence versus the Auger decay. Yes, and well, that's this one is only for the K-shell vacancy. That's true, and well, that's why we just develop like a simple model to approximate the rates and to find out the relation between rate and the atomic number G. And well, since both of them are started from the inner shell vacancy, so the incoming photon energy does not enter in this case. Well, on the other hand,
oh, sorry.
Oh yeah. Well, yeah. All
there
right.
are two more questions. One of them is there any probability for having a KLM Auger decay?
Sure, of course, there are. All possible, yes. And as you can see here, well, I didn't mention it, but the dotted line purely corresponding to KLL, and the solid line here indicates KLL, KLM, KMM, KNN, and so on. So all contribution. Yes, those are all possible. That makes quite complicated. Yes.
And then maybe a last question. How would you calculate the relative rates of competing Auger decay channels? Is it mostly dependent on the overlap of the initial hole and the final hole?
Well, I would like to say that depends on the this Coulomb interaction. So a Coulomb interaction, well, involving the core, the inner shell vacancy, and the two valence vacancies, and also the continuum states. Those are all involved.
Okay, thank you. There are no more questions.
All righty. And okay, I have a question for you guys. That's another quiz. Decay showdown. Okay, well, we just saw the K shell vacancy, but what about the L shell vacancy? That's the other question. And well, still, do you think do you think the fluorescence is dominant, or in this case, Auger-Meitner channel wins? Or if you want, still you have a chance to choose equally probable or no decay. What do you think?
Okay, I'm gonna end the polling, and you should see the results now.
Yes. Well, the half of you guys, half of people chose Auger decay. And yes, in this L-shell vacancy, yes, it's Auger decay wins. As you can see this plot. And this is calculated using the X atom with our rate formulas we just learned before. And here I'm plotting the only 2s vacancy, but it's pretty much same for the other 2p vacancy and so on. So well, depending on which subshell you are talking about, which inner shell vacancy you are talking about, so you have to calculate the rates, decay rates, to know which channel would be the dominant case. It has an important implication. I already mentioned to you. So well, that's Auger cascade. Maybe we should call it Auger-Meitner cascade. Well, on the left side, as you can see, the light atom, the Auger decay makes neon 2+ at the end. Like at maximum, it can be a neon 3+ after the double Auger decay process. But mainly, the single photon absorption makes neon 2+ after one Auger-Meitner decay. On the right side, the heavy atom case, well, not only the LMM channels, but all well, let's start with the LMM channel, which makes the 2 M shell holes, and 2 MNN decays make the 4 N shell holes, and so on. But well, again, this is not the end of the story. So there are many combinations like LMM, LNN, LNO, LLOO, and so on. So a series of Auger decay processes happen after one single photon absorption. This is called Auger-Meitner cascade, which makes ionization dynamics of heavy atom so complicated. Okay, well, the next topic is elastic X-ray scattering. And well, this is, previously, someone asked us like absorption plus the fluorescence can be considered as the scattering process. But here, this the scattering process is different from there, because here the initial electronic state and the final electronic state are the same. That means that makes elastic scattering. And well, in this case, well, the dominant channel throughout the A square term rather than P dot A. So in the interaction Hamiltonian here, it's, well, we're gonna use A square term in this case. What else I'm missing? Oh, here, the photon state. We started with the N photon, N incoming photons, and in the final, we have N-1 photons plus 1 scattered photon with KF. That's gonna be the final state. Once we plug in, then the rate is expressed like this. And okay, the K in here is incoming wave vector, and KF is outgoing wave vector. So the difference between them is defined by the momentum transfer Q. And the rate is proportional to F square, and F is called scattering form factor, which is given by the Fourier transform of electronic density. Likewise, the absorption expression, it's more convenient to consider the cross-section rather than the rate. So the cross-section is given by the rate divided by the incoming flux, and well, the cross-section here at the end, it's given by the form factor modulus square. Once we measure the scattering cross-section, we obtained molecular form factor, actually the magnitude of the other form factor. And then, well, if it is possible to, well, obtain the phase of molecular form factor, then there is a chance to reconstruct the electron density. Here, the molecular form factor is, well, it could be decomposed into the, decomposed into the atomic contribution, and we can calculate the atomic form factors. Therefore, well, there is a way to obtain the atomic position here, the Rn, from the scattering measurement. This is an exemplary figure of atomic form factor for krypton, and this is nothing but a Fourier transform of atomic electron density. When an atom is exposed to X-ray, it undergoes either absorption or scattering, or nothing happens. Which one would be the most probable? Well, if we know the cross-section, then we can easily answer such a question. That's why the cross-section calculation is so important. For the carbon atom at 10 keV, the absorption cross-section is about the 13 times higher, 13 times larger than the scattering cross-section. So the absorption is typically dominant in the hard X-ray regime. Here is a classification of X-ray scattering processes. Depending on whether the initial and final electronic states are the same or not, we can categorize elastic or inelastic. Depending on whether it involves intermediate states, M or not, we can distinguish the first order of A square dominant or the second order of P dot A dominant. For elastic X-ray scattering, the non-resonant scattering happens via the A square, but when the photon energy is close to the ionization edge, the resonant contribution becomes important via the second order of P dot A, which is called dispersion correction. It corresponds to the anomalous scattering. For inelastic X-ray scattering, the non-resonant one is called Compton scattering, treated by the A square term. And the resonant inelastic X-ray scattering happens via the second order of P dot A, which is called RIX as an abbreviation, or resonant X-ray Raman process. Here's another quiz. So let's think about the scattering probability, which is given by the cross-section times photon fluence. Photon fluence is defined by the number of photons per unit area. Typically, the scattering process is extremely small. Like for example, here, the carbon at 12 keV, and with the typical fluence from the synchrotron radiation, the probability is about 10 to the minus 12, which is extremely small. How shall we increase this tiny probability? A is just prepare more targets. B is throw the more photons. C is there's no way. Well, you may take multiple answers if you like. I should say this one first, but anyhow.
Unfortunately, this Zoom polling is not set up to take multiple answers, so you will people will decide for one thing. Unfortunately.
Let's see the
okay
what people chose. Yes, now it's a real interesting. Wow. Wow, I see. Well, the almost 2/3 of the audience chose throwing more photons. Oh, yes, that's the obvious choice. We just throw just more photon to get the more signal. Yes, and well, and 24% of the audience chose to prepare more target. I think that's also possible, as shown here. So I would like to choose answers are 2, A and B, and the A just um, preparing the identical targets, which make the scattering signal added up coherently, and that's actually the basis of the X-ray crystallography. And the other way around is B. I mean, we just throw more photons, and that's actually the concept of XFEL. So just increase the X-ray intensity. And well, in this way, we may not need to make a good crystal. The issue is, well, the making a good crystal is extremely tedious task, as I heard, and most of proteins do not make a crystal, do not form a crystal. So that's why, I mean, well, this is the biggest motivation to develop XFEL facilities. Again, well, we have to remember that the absorption cross-section is higher than scattering cross-section in the photon energy regime where the X-ray scattering experiments are conducted. So we need to understand the X-ray absorption mechanism. In other words, radiation damage mechanism when we use intense X-ray pulses for the molecular imaging. Okay, well, here, this is the very much simplified procedure of the X-ray crystallography. The making protein crystal, well, that's extremely difficult. But once we have the crystal, then we measure the scattering pattern and obtain the modulus of the molecular form factor. If we are able to obtain the phase information, then we have a full molecular form factor, and taking the inverse Fourier transform, we will get the electron density. From there, we can determine the atomic position in a protein. Well, that's the very simple story of X-ray crystallography, but I hope you can hear much more fascinating story from the Petra Frome on Thursday's lecture. Okay, well, so far we have explored all about X-ray induced processes. Well, I would like to stop here and let's take the 3 minutes break. Okay?
Perfect. There is one more question which I kind of delayed so that you could continue, but maybe you want to answer that briefly. I think it still refers to the Auger-Meitner process. The question is, why is there only one electron ejected? Is it possible to emit 2 or more electrons?
Well, simple answer is yes, it is possible. If it ejects 2 electrons, this is called double Auger decay. Or we can say double Auger-Meitner process and so on. Yes. If it ejects 3 electrons, and we may say triple Auger decay, I remember I heard of it. Such a process. Yes. Mm-hmm.
Yes, that's all the questions which were there so far.
All right. So, well, after a short break, I will talk about the high intensity X-ray physics. Yeah, let's see.
Nice. Yeah, so we currently have about About 150 people on the Zoom meeting and another 55 people on YouTube. So
55. Wow.
yes.
I see. Interesting.
As an information for the audience, Sankil also used to organize and chair the summer school some years ago.
I think that's a 2015.
Yes.
Yeah, in Hamburg. Yes.
I was actually an attendant.
Sorry, you?
I attended the summer school.
What? 2015?
Yes.
Oh, I see. I'm sorry, I have to remember. I mean,
No worries.
wow. Well,
yeah, time is flying.
I must tell. Yeah. Well. Oh, yes. So, shall we start again?
Sure.
Yes. Okay. What happens if X-ray intensity is so high? Well, let's talk about XFEL science, XFEL AMO science. So first, what do I mean by high X-ray intensity? We learned that how to calculate photo absorption cross-section. That was the one photon absorption via the first order correction of the time-dependent perturbation theory. So the cross-section times photon flux, photon fluence provides a probability. When the probability is close to the 1, and then we say it's saturated. One photon absorption is saturated. The fluence to saturate one photon absorption is given by the inverse of photo absorption cross-section. The plot shows, and this plot shows the number of scattered photon as a function of incoming photon fluence. In the low fluence regime, here it's linear. This is a double logarithm plot, and the slope of this is just 1. However, in the high fluence regime here, well, higher than this saturation fluence. The outcome, the number of scattered photon, shows non-linear behavior because it starts to observe more than one photon after saturation point. The high X-ray intensity means here that it's beyond one photon absorption saturation, which basically means when it observes more than one photon, it observes many photons during an intense X-ray pulse. And we should expect multi-photon process and nonlinear behavior. As we already learned basics of X-ray matter interaction, the photoionization here, P, is followed by Auger-Meitner decay, A, for the light atom case. And well, when many photons are observed, this sequence, like a PA, happens several times, like a PA. At the end, the carbon can be fully stripped to the bare nucleus, carbon 6+. In high intensity X-ray regime, the multi-photon ionization happens via sequential multi-photon multiple ionization. This is the seminal work, the very first X-ray field experiment of neon atom, led by Linda Young. Depending on X-ray photon energy, the different sequences occur here, and there. But anyway, where it reaches very high charge states like neon A+ or neon 10+, via the sequence of P, A, and V. The V is like valence ionization. As a result of X-ray atom interaction, the right panel here shows the ion yield as a function of charge state, so-called charge state distribution, making the comparison between theory and experiment. This was the great achievement. It's an excellent agreement in spite of a lot of uncertainties in both theory and experiment. In the same paper of neon and the seminal paper of N2, the experimental data demonstrated a very intriguing phenomenon. Let's check out the bottom panel here. This is the average charge as a function of pulse duration. And the pulse duration becomes shorter and shorter, then the average charge is reduced. Think about it. The shorter pulse duration means higher intensity. But higher intensity makes less ionization. It sounds totally counterintuitive. And this is called intensity-induced X-ray transparency, or the frustrated absorption. Why does it happen? Well, we can explain it with hollow atom formation or the double core state formation. After one photon absorption here, then it makes a single core state like this. And we learned that how to calculate the Auger rate. If you take the inverse of Auger rate, then you will get a lifetime. In this case, it's about 2.5 femtosecond for the neon single core case. If the pulse duration is comparable or it's shorter than this lifetime, then there is a chance to observe another photon before it decays. It makes here, and it makes the double core state, and there is no more K-shell absorption here because no more K-shell electron remains. Therefore, the double core formation makes absorption cross-section reduced, which makes less ionization. It would be very much beneficial for the purpose of molecular imaging because it could reduce the electronic radiation damage by using shorter pulse. As you can see below here, the ratio between the scattering and absorption cross-section here, that ratio becomes increased for the single core hole and double core hole states. Okay, well, here is a kind of illustration what I want to talk about. This is a plot of the mean charge of xenon at 5.5 keV as a function of fluence. And here is a saturation, the fluence point at this photon energy. And the typical fluence of synchrotron radiation is about 10 to 4 or and so on. So it's way below here. The previous neon and N2 experiments at UXSS were around here. And another X-ray field experiment of xenon at 5.5 kV, the same condition, at the SACLA was about here, this point. So now in the upcoming slides, I will present some results around this high fluence regime, where we could see a fascinating phenomena. And at the end, I will show the new results at the extremely high fluence here. Okay, well, we've already seen the heavy atom undergoes very complex ionization dynamics, and even after single photon absorption. But now, when it observes many photons sequentially, you may imagine how complicated it would be. So here, the X-ray fluence is much higher than before, much higher than were used in the early X-ray field experiments. And now the maximum charge state reaches about, well, 35, well, 40, well, higher than 40 plus. The new phenomena here are resonance-enabled enhancement of ionization from here to here. And the peak structure modulated by relativistic effect. The black dots here black dots are the experimental data, and all others are theoretical results with some combination of the different treatments. Only when we include both resonance and the relativistic effect, which is red one here, boom, 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 it's nicely matched with experimental data. It shows that the synergy effect of the resonance and relativistic effect.
Dankil?
Yes?
Do you think it's possible to answer a few questions to these really high intensity ionizations, or do you want to continue?
Well, let's take the question.
Okay, so do we call that a multi-electron excitation?
Multi-electron excitation. Well, if you think about the core hole states, if you think about multiple core hole states, that means, I mean, not only one core hole, but there are many core hole inside, then it's a multiply excited system. So, well, in this sense, you may say it's a multiply excited system. Yes. I mean, if you are talking about multiple core hole state.
Okay. And then a second question, does it depend on the pulse length or on the photon density?
Both, actually. So I just, to emphasize, well, in connection with the Auger lifetime and so on. So that's why I just mentioned the pulse duration only. But in fact, well, the photon flux, in other words, like the fluence matter. So, well, basically, we have to calculate Auger rate, or well, actually, Auger rate is independent of the photon flux or the fluence, yes, but we have to calculate the photo absorption, the second times of the photo absorption rate, which is given by the cross section times photon flux, yes. So, and then we have to compare Auger rate and photo absorption rate, and which one would be the dominant to create the double core hole. It's very true. So we have to take into account both of them.
Okay, and then another question is, what are the chances for one atom to absorb 2 photons in a short pulse?
Well, if it asks like a direct 2 photon absorption, I think, well, the answer is yes, it is possible, but the cross-section of direct two-photon absorption is extremely low. So that's why if one photon channel is available, then it's always win in the X-ray regime. I mean, well, I shouldn't say always. So in the regime of the current XAFL facility, the single photon absorption is dominant if that's available. And if you are talking about sequential two-photon absorption, and that's what I'm talking about. I'm talking about multi-photon absorption, sequential multi-photon absorption. Yes, it's always happen.
Okay, and then somebody was asking if this is if there are relativistic effects taking place.
Actually, in the previous slide, yes, it does. So just to point out the gray one here is non-relativistic treatment, and then we have 4 peak structure. But in fact, when we use the relativistic electron structure calculation, we have 3 lobes or 3 peaks. That I remember that twist transition and 3p 1/2 transition and 2p 1/2 transition and 2p 3/2 transition. So 3 peaks corresponding to 3 peaks corresponding to 2s and 2p 1/2 and 2p 3/2. So that's the signature of the relativistic effect in the xenon electron structure calculation.
Okay, and
yes,
yeah, maybe one last question, and then we probably should let you go on. When multi-core holes are generated by high-intensity X-rays, what happens to the valence electrons and their chemical bonds with other atoms, let's say in a molecule?
Well, that's a good question, and then I will show the molecular case in the next slide. And then I hope that it will answer those questions.
Perfect, then let's go on.
Yes. Well, what happened to the molecular case here, like for example, iodomethane case, a molecule contains a heavy atom like iodine. Well, the issue is the xenon atomic number is 54, and the iodine atomic number is 53, have a very similar photoabsorption cross-section. And and we might expect we might have the same degree of ionization for both cases. Well, the thing is, the cross-section of the iodine here, it's much higher than all other light atom here. So here you can see the cross-section values. So that's why the ionization happens almost exclusively on iodine only. Again, it creates very high charge states like 30 plus and 40 plus and so on. And well, this highly positive charge on the iodine is shifted and rearranged among the methyl group, and eventually it breaks apart due to the Coulomb explosion. How do we consider this ionization dynamics and charge transfer, what electron transfer from the neighboring atom dynamics and the explosion dynamics? This is the main theme of this paper here. And for the charge state distribution plot here, where we can learn the ionization dynamics, and for the kinetic energy plot of iodine fragments, where we can learn the details of fragmentation dynamics. For both of them, we have an excellent agreement between theory and experiment. And this is the first quantitative comparison for the dynamical behavior of polyatomic molecules under XFER radiation. Based on this good agreement, yes, we investigate a fascinating phenomena here, so-called CREXIM, the charge rearrangement enhancement enhanced X-ray ionization of molecules. The selective ionization induces charge imbalance, and charges are rearranged, well, meaning that the electron from the methyl group are transferred to the iodine if this is a single one photon absorption. Then the process would stop here. Then the charge rearrangement cannot enhance the total charge. However, we are in the sequential multiphoton regime, so this type of thing happens again and again. So electron transferred from the methyl group to the iodine could be further ionized on the iodine side. See this plot here. So this is a mean charge as a function of fluence. And the black one is independent atom model, assuming that there is no chemical bonding among the atoms. And red one is full molecular calculation. At the low fluence here, there's no difference. No difference between the atomic and the molecular picture. But as fluence increases, now the difference becomes clearly visible. In a molecule including heavy atom, it ionizes dramatically and it sucks the electron from the neighboring atom, thus being the more ionized than the corresponding atomic case. This was the story of the molecular case. And now, well, we learned, the previous slides, we learned that the frustrated absorption in the matter, but there is a chance that it breaks down when we achieve extremely high fluence. This plot shows the mean charge as a function of pulse duration here for the different fluences. The red one shows as the pulse duration decreases, then the mean charge drops down. That's a typical trend of the frustrated absorption. However, when we have extremely high fluence, like a blue curve here, so the trend becomes totally opposite. The pulse duration goes down, decreases, then the charge goes up rapidly. Interestingly, it can be also explained by hollow atom formation combined with the a detour of ionization pathway. So if we achieve like terawatt attosecond XFL pulses, in other words, extremely high intensity X-ray pulses, then this anti-frustrated absorption behavior could be a critical benchmark, in my opinion. So for the attosecond XFL pulses, you will hear more by the James Cryan after my talk. Okay, well, this is a summary of the multiphoton ionization at the high X-ray intensity. The left is atomic case and the right is molecular case. And both of them shows the mean charge as a function of the fluence, and the low fluence, it's well, one photon absorption is dominant. So basically the ionization is linearly proportional to the cross section. So we just learned that the higher photon energy gives lower cross section, therefore lower mean charge. But when you get the higher fluence, it becomes opposite. For the molecular case, yes, at the low fluence case, xenon and iodomethane, iodobenzene, they are more or less the similar cross section, therefore similar the mean charge at the low fluence case. But when you get the higher fluence, then they deviate to each other, and the iodobenzene becomes much more ionized than iodomethane and xenon case. Also, with the extremely high intensity and the ultra short pulse, like a terawatt attosecond pulses, I would expect to see the breakdown of frustrated absorption. The last slide is some reference for you. And well, if you want to have the data table, then you can check out this useful booklet. If you are interested in the theoretical aspects, you should go through this excellent tutorial paper of the X-ray physics by Robin Santra. And the most of the equation in my slides came from this paper. If you are a fan of the computational stuff, you can go and ask a permission of XLM toolkit. And I also include some latest references for high intensity X-ray physics that we have explored together. So with that, I would like to say thank you so much for your attention.
Thank you, Sankil. Thank you so much. And I don't know how you did it, but with all the questions, you even stayed on time. There are a few more questions, and I think we can eat a little bit into the break and answer some of them. And then I would refer the rest of the question, the participants who asked them, to the office hour, to your office hour later today.
How many questions do you have right now?
At the moment, about 9.
I think, yeah, well, I think we have to put them into the office hour.
To the office hour. Okay. Yeah. Then please, everybody who asked these questions, write them down. Don't forget them, and join Sankil later today in the office hour.
Yeah, welcome to join the office hour, and we must take 30 minutes break. So the 30-minute break. Sorry about that.
Perfect. Yes, then Sankil, thank you again. This was really a pleasure to listen to the lecture. And let me see. There's also some response from the audience. So not all of the questions which are coming in are actually questions. There are a lot of thank yous to you.
Nice. Yes. It's my great pleasure.
So yeah, thank you again. And then with this, I will close this session for the participants. There is another break session like yesterday, and we will reconvene on the Zoom webinar with a different Zoom link at 10 a.m. for lecture number 3 by James Crine. Thank you all. And
thank you.
With that, I'm gonna close the live stream and stop recording.